Right now, at this exact moment, there are roughly 50,000 cargo ships out on the ocean. Billions of tons of steel, grain, fuel, and electronics, all moving silently across the planet while you sleep. Think about the phone in your pocket, the shirt on your back, the coffee in your cup. Almost none of it was made anywhere near you, and yet all of it arrived on time, intact, and impossibly cheap. That didn't happen by magic, it happened because of physics. This is the invisible machine that runs the modern world, and once you understand how it actually works, the hulls, the rails, the cranes, the mathematics of moving mass, you'll never look at a container ship or a freight train the same way again. So let's break it down. Start with the biggest number in this entire story. Somewhere between 80 and 90% of everything traded on Earth by volume moves across the ocean. The sea wins because water is the cheapest surface in the universe to move heavy things across, and the reason comes down to pure physics. When a ship pushes through water, it fights drag. But here is the beautiful part. As you make a ship bigger, its cargo capacity grows faster than its resistance does. Capacity scales with volume, while drag scales roughly with the wetted surface of the hull. Volume grows as a cube, and surface area only grows as a square. Double the size of a ship, and you do not double the drag. Instead, you get more cargo per unit of resistance, more freight per liter of fuel. The bigger the ship, the better the math gets. Shipbuilders chased that math for decades, and it produced monsters. The largest container vessels afloat today carry more than 24,000 20-foot containers, stacked on a hull longer than 4 football fields laid end to end. And the economics that fall out of that scale are almost absurd. A single 40-foot container holds thousands of individual products, so when you spread the cost of the voyage across everything inside, crossing the entire Pacific Ocean adds just cents. Maybe a couple of dollars to the price of each item. The ocean leg of a television's journey often costs less than the cardboard it's packed in. That's not a rounding error. That's the foundation of globalization itself. When moving something 10,000 kilometers costs almost nothing, geography stops mattering, and factories can be anywhere. But ships have a problem. They can only go where the water goes, which brings us to land. Before we leave the port, though, we have to talk about the single most important invention in the history of trade. It isn't the ship, and it isn't the engine. It's the box. Until the 1950s, cargo moved as what the industry called break bulk. Loose crates, barrels, and sacks loaded by hand, one piece at a time. A ship could sit in port for a week just being unloaded, and loading the cargo often cost more than sailing it across an ocean. Then, in 1956, a trucking entrepreneur named Malcolm McLean asked a deceptively simple question. What if the cargo never got touched at all, and the entire truck trailer, minus the wheels, just lifted off and dropped onto a ship? And that's when the standardized shipping container was born. Same dimensions everywhere on Earth, same corner fittings, same locks. A steel box that a crane in Shanghai, a train in Chicago, and a truck in Rotterdam could all handle without ever opening it. The result was staggering. Port loading costs collapsed by more than 90%. Ships that spent a week in harbor now turned around in hours. Theft plummeted, insurance dropped, and the price of distance essentially evaporated. Every system we're about to look at, the rails, the trucks, the planes, the ports that connect them, is built around this one humble object. The box is the atom of global trade. Once cargo hits land, a new champion takes over, and its superpower is friction. Or rather, the almost total lack of it. A steel train wheel rolling on a steel rail is one of the lowest friction contact systems ever engineered. The contact patch between wheel and rail is about the size of a small coin. Compare that to a rubber truck tire, which deforms and grips and drags against the asphalt with every single rotation. The consequence is staggering efficiency. A modern freight train can move 1 ton of cargo roughly 400 to 500 miles on a single gallon of fuel. Read that again. 1 ton, more than 400 miles, 1 gallon. Trains scale the same way ships do. One locomotive crew can haul over 100 cars, thousands of tons, in a single movement. Double-stacked container trains, 2 boxes high, stretch for kilometers across continental interiors, doing the work of hundreds of trucks with a tiny fraction of the fuel and labor. Rail is the ocean's partner on land. It's brutally efficient, but rigid, because trains only go where the tracks go, and the tracks don't go to your street. Which brings us to the least efficient mode in the whole system, and the one that nothing else can replace: the truck. Per ton mile, trucking burns far more fuel than rail or sea. One driver, one engine, maybe 1 or 2 containers. On pure physics, the truck loses every single comparison. But freight isn't only a physics problem, it's a geometry problem. Ports are points on a map, and rail lines are lines. Customers are everywhere, scattered across millions of addresses that no ship or train will ever reach. Trucks win because they go where the infrastructure ends. Every warehouse dock, every construction site, every store on every street exists inside the trucking network. That's why the industry calls it the last mile, and it's why the last mile is often the most expensive part of a product's entire journey, even after that product has already crossed an ocean. So the global system isn't a competition between modes. It's a relay race. Ships handle the oceans, trains handle the continents, and trucks handle the final handoff. And for a tiny slice of cargo, there's a 4th runner. By volume, air cargo is almost invisible, less than 1% of global trade. But measure by value instead, and the picture flips completely, because roughly 1/3 of everything traded in dollar terms flies. That's more than $8 trillion worth of goods every year. Some cargo is simply worth more than the fuel it takes to defy gravity. Smartphones and semiconductors worth thousands of dollars per kilogram. Pharmaceuticals and vaccines that expire, fresh salmon, cut flowers, and urgent spare parts for a factory line that's losing money every idle minute. Air freight is the system's expensive insurance policy. When the value density is high enough, or the clock is unforgiving enough, physics takes a back seat and speed writes the check. Now here's the twist that most people never see. The bottleneck in global freight usually isn't the ocean crossing, the rail line, or the highway. It's the handoff. Every time a container changes modes, ship to crane, crane to train, train to truck, the entire system holds its breath. This is intermodal transfer, and it's where the world's ports are won and lost. The best port cranes on Earth can pluck a container off a ship roughly every 90 seconds. That sounds fast, until you remember the ship is carrying more than 20,000 of them. Multiply it out, and crane speed, yard layout, and scheduling software determine how long a $200 million vessel sits idle at the dock. Zoom out further, and you'll find the routes themselves are shaped less by distance than by choke points and conditions. The Suez and Panama canals compress thousands of kilometers of sailing into narrow, contested corridors. Weather routing bends paths around storms to save fuel, and fuel prices redraw the map of what's even worth shipping at all. Global freight, in the end, isn't one machine. It's thousands of machines, hulls, rails, tires, wings, and cranes, all synchronized by a steel box and a schedule. So the next time a package lands on your doorstep, picture the relay behind it. A crane in a foreign port moving on a 90-second rhythm. A hull designed around the mathematics of drag. A train sliding a ton of cargo 400 miles on a single gallon of fuel. A truck finishing the job that no other machine can. It's an invisible system running day and night, built on physics most of us never think about, and it works so well that we forget it exists. That's how the world moves. If this changed the way you see the machines around you, hit subscribe, because on this channel we break down the physics behind everything that moves. See you in the next one.